Hello, my name is Audrey Munger, and this is my lab number 4 on magnetic braking with Faraday. So starting off with the introduction section, in this lab, a bar magnet is dropped down a tube of aluminum foil, and then I timed each drop for 5 rounds. And the main goal of doing this experiment is to observe how Faraday's law comes into effect during the interactions of a bar magnet and aluminum foil as it's falling down the tube. And the system will be the bar magnet and the aluminum foil tube, and the surroundings is Earth and anything else that's around it. Two fundamental physics concepts that are important to understand the lab are Faraday's law and the Biot-Savart law. So Faraday's law, it describes the magnitude of the electromotive force in a conductor due to changing magnetic fields, and it's described with that equation right below it. The second, the Biot-Savart law, that one we've gone over in a previous lab, but it describes the magnetic field generated by a constant electric current, and its equation is also below it. Okay, so for my observational model of me actually dropping the magnet down the aluminum foil tube, my initial conditions are seen here on the left. I've just got the length of the tube, width of the tube, the radius, and then the mass of the magnet. And then the procedure I used for that is first I had a tube of aluminum foil and it was set up vertically, and I dropped a magnet down the middle of it with the north end of the magnet down. And then just so I could get like a more accurate reading of the time, I recorded a video of it so I could like use the frames and the timing to find the exact time of the fall. And I repeated it 5 times and took the average time. Here are the results for each of my 5 drops of the magnet down the aluminum foil tube. They were all similar but slightly different, so I took the average and got 1.45 seconds. You can see here some of my GlowScript code to make a computational model. I added in the same initial conditions that I had 2 slides ago from my observational model, and then you can see we coded to calculate for the magnetic field and the magnetic flux. I also coded to find the magnetic force and the gravitational force and use those to find the net force, which allowed to solve for time it took for the magnet to fall down the tube. Here are the results from my GlowScript model. There's a picture on the left, and then the graph on the right shows that the time calculated was 1.16 seconds. Now looking at the results from both my observational and my computational model, the fall time from my aluminum foil experiment was 1.45 seconds, and the time in the GlowScript code was 1.16 seconds. So these are a little bit off, and the difference in time could be due to mistakes in my experiment, like miscalculating the resistance in the tube, or miscalculating the initial conditions, or maybe errors in my timing from my observational model. Now finally, looking at the what if questions, the first one says, what if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of a falling magnet change? This would make the magnet fall down the tube more slowly. The induced current in the tube would become larger, causing the magnetic field and magnetic force on the magnet to also be larger. The second question asks, what if holes or slots were cut into the tube? How would this affect the ring currents in the model? So holes or slots in the tube would disrupt the induced current flowing through the tube, making the current slower. This would also make the magnetic field be lower, so the magnet would fall down the tube faster this way. Thank you so much for watching my lab video. I'm sorry if there are any thunder noises in the background. It's storming outside right now.